Però questo è l'ultimo. Okay. È un momento solo per... The floor is yours. Okay. Thank you. Good morning, everyone. This talk is focused on the theoretical investigation of the charge exchange reaction, particularly important for the unveiling of the dynamic of gas phase bimolecular reactions. This work is part of the Vitality project, in which the University of Perugia is partner, and the main goal is to develop a new generation of nanomaterial with a wide range of application, going from energy and hydrogen storage to medicine and carbon neutrality technique. So in principle, the two topics can be a bit unlinked, but we can see that in order to develop this task, we need a detailed understanding of the fundamental interactions. So in order to develop new formulations of the potential and to test their efficiency, we have to look at very small systems in which we can focus on the particular interaction that we want to study. And the best candidates are gas phase bimolecular processes, because in this case we have the chance to investigate the single phenomena without the interference of other processes, such as the influence of solvent and so on. And gas phase processes has a wide range of application, going not only from material sciences, but also from atmospheric chemistry and astrochemistry, which is the focus of the presentation of today. Very briefly, the astrochemistry is a quite new branch of science which mixes different fields, going from astronomy to chemistry and data modeling, in order to try to understand the first stages of the evolution of stellar systems, which are similar in some cases to our solar systems. As we can see in this picture, the process of star formation is a cyclic process which starts from the aggregation of the diffuse clouds, going to the formation of new stars, and when the lifetime of the star ends, it basically ejects all the material synthesized, and the cycle starts again. There are 5 major phases for the formation of sun-like star-forming, sun-like stellar systems, starting from a diffuse clouds. And thanks to the gravitational attraction, we have the moving of all the material toward the center, and when the density at the center is enough, we have the formation of the new star and the related disk in which there will be formed the planetesimals and then the planets. As we can see, thanks to the new facilities of astronomical observation, we see that the molecular complexity in all the stages is increasing, and somehow all the chemical information is stored and conserved through all these phases. And the also complex molecules which are formed can be delivered on the new planets thanks to different processes, such as the collision with comets, meteorites, and asteroids. So in some way, prebiotic molecules on Earth can be inherited from interstellar species. Different phases of star formations are linked to different chemical and physical properties and conditions, and in general they can be prohibitive for molecular growth because the temperature is very low. It can reach also 7 or 10 Kelvin, and the particle density is around 10 to the 4 particles per cubic centimeter. So despite this very harsh condition, a wide range of molecules have been detected, also going from simple but also complex species containing up to 60 atoms. In particular, they are both neutral and ion, and they are also unsaturated hydrocarbons. So despite the prohibitive condition, we have different molecules, and we want to understand how they are formed. There are 2 main formation mechanisms related to the chemistry taking place on the surface of the grains, which are sub-millimeter sized materials which are present in the interstellar medium, and their surface can act as a catalytic site for the synthesis of complex molecules, which are then released in the gas phase and can react to form more complex species. So all this information are used to fill astrochemical models, which combines outcomes from astronomical observation and experimental and theoretical data. So a detailed characterization is essential in order to have a meaningful astrochemical database which contain both formation and destruction routes. And in this talk, we will focus on destruction mechanism, mainly driven by ion-neutral reactions because they are faster and more efficient than neutral processes. Ion-neutral reactions mainly involve a first charge transfer process leading to the formation of a new chemical species, which can then fragment and form different ion and molecules. The main collision partners are H+, helium+, H3+, and HCO+, which are formed through the interaction of neutral molecules with different sources of energy. In the actual astrochemical databases, there are more than 8,000 chemical reactions included, but the main problem is that most of them are included with the parameters which are necessary to derive the rate constant based on estimation methods, based on chemical analogies with similar system. So a systematic work is essential to have a reliable astrochemical database. So in this work, we started the reaction of the Helios plus cation with the acetonitrile molecule, which has been detected in different regions of the interstellar medium, and it's also important because it can be linked with more complex and prebiotic species containing a CN group. In particular, we combined an initial approach based on DFT calculation with a semi-empirical investigation based on the improved Lennard-Jones formulation, which has been developed at the University of Perugia. And the same computational strategy has been already tested in previous analysis with the same reaction partner, which is helium plus. We started by defining the coordinate system of our process, and in particular for the acetonitrile molecule, we consider three different moieties, the C and N atoms of the cyano group, and an effective carbon atom which takes into account all the effect of the CH3 group. And we defined the helium plus cation by polar coordinates, considering a distance r from the center of mass of the molecule and an angle theta. So using this system through the Carnot theorem, we could easily derive the distance of the helium plus through the three moieties of the acetonitrile molecule. And in order to derive the potential, the interaction potential, we use the improved Lennard-Jones. The improved Lennard-Jones is a new formulation developed at the University of Perugia, which is similar to the classical Lennard-Jones potential, but it's improved in the sense that it is able to have a better representation of both long-range attraction and short-range repulsive forces. As we can see, the formulation is similar. We have an attractive and a repulsive contribution, but we have three new parameters which are directly linked to fundamental properties of the system, such as dipole and quadrupole moment and atomic and molecular polarizability. And this link leads to a high degree of transferability of the potential. So once we tested the formulation for simple system, we can easily, and with a low computational effort, move to more big and complex systems. Here I reported, just for information, the structure of the codes that have been written in order to calculate the potential energy surface with the improved Lennard-Jones analytical formulations, which has been already presented in the last ICCSA conference in the last year, and I have here the reference if you want to check. Basically, we have an input of the coordinate systems using the polar coordinates and all the improved Lennard-Jones parameters. We have also an electrostatic contribution, which is calculated considering atomic charges, and in the output, we have the analytic formulation of the potential energy surface. So first of all, we optimize the geometry at the B3 level with the triple zeta basis set in order to obtain also atomic charges and bond distances and angle. The optimized geometry has been then used to calculate the energy of the molecular orbitals since experimental data were not available. And if we compare the energy of the orbitals with the ionization energy of helium plus, which is the highest in the periodic table, we can see that the electron transfer from the HOMO, highest molecular orbital, is not possible because will lead to an inefficient adiabatic coupling since it's exothermic. So in order to have an efficient process, we have to have the condition in which an electron is ejected from the HOMO -6 orbital, whose shape is reported here in the slide, and we can see the presence of a nodal plane in the carbon of the CN group. Then considering the same coordinate system using polar coordinates, using also the cylindrical symmetry, which allowed us to decrease the dimensionality of the problem, we derived the parameters from the improved Lagrange formulations, and from that we could derive the potential energy surface of the process. Here we have a 3D representation in the x-zeta plane for the entrance channel, so helium plus CH3CN. And we can see that the system is strongly anisotropic, and the favorite orientation is the one where the helium plus approaches the CN group of the acetylnitride molecule. Then with the same formulation, we could derive the analytic potential energy surface for both the entrance channel and the exit channel, which is the channel after the charge transfer process, so neutral helium plus CH3CN plus. And we can see that in the entrance channels there are barriers with whose heights increase as air decreases. And the presence of these barriers under thermal and subthermal conditions leads to an insurmountable orientation due to the rotational motion of the CH3CN molecule. So we have a strong anisotropy of the system, and the favorite orientation is strongly driven by the presence of these barriers. Finally, in order to properly characterize the reaction dynamics, it's important to study the crossing between the entrance and exit potential energy surface. So as we said before, the ionization energy of helium allowed the ejection of electrons from the almost -6 orbital, and we derived here the potential energy surface from the crossing between the entrance and the exit pass. And we can see that for angle theta higher than 90 degrees, the crossing is not present anymore, which is another evidence of the effect of the symmetry and of the orientation of the initial approach. So in the next step will be the use of the crossing, of the position of the crossing to evaluate the probability, and then the cross-section for the charge exchange process through the Landau-Zener approach, which allow us to derive the total cross-section of the process, considering the non-adiabatic coupling, which leads to the calculation of the probability of crossing. And then we are now comparing our theoretical results with the experimental analysis performed at the University of Trento through the gas phase experiments for measurements of ion-neutral interaction facilities, which allows to obtain total and partial cross-section as a function of the collision energy of the system and the product branching fractions. And in particular, we can see that the match between theoretical prediction and experimental analysis is very good. So the two data are very in line and will allow us to easily derive the cross-section of the process. So in conclusion, we perform a theoretical investigation of the charge exchange process of the helium plus CH3CN reaction as possible destruction mechanism for ions using a new formulation of the potential, which is improved Lagrange, which allow us to easily move from a system to another thanks to this high degree of transferability. So the next step will be the detailed investigation of the reaction dynamic in order to derive the total cross-section and the rate constant which will be used in the astrochemical model. Thank you for your attention.
Thank you, Luca. Okay, I stopped the time. So if you have some questions, I don't know if there is online someone.
No.
No?
There are no questions from the virtual room.
Okay, so I asked you a curiosity. if you compare or are you working about the comparison about the rate constant with the experimental results? There is a value of the experimental results or not yet?
Okay, the experimental results are different. We have the branching fraction of the old channels that they derived during the experiment, which cannot be directly compared with our calculations, but we have the comparison with the cross-section. So they are able to obtain the total cross-section, which is compared with our data, and the agreement for the moment is very good. So once we have this agreement, we can use our prediction to go also to lower energies, which are representative of the low temperature of the interstellar medium. So our calculations will help us to elucidate that value, which is not possible with the experiments.
Okay, perfect. Thank you very much. So now we move to the next speaker, Dr. Parriani. Sorry, but mettimi la condivisione così almeno lo leggo perché. Ok. Okay, Marco Parriani from University of Perugia, Department of the Engineering Civil and Ambiental, and he will speak about the data analysis of molecular degradations, fragmentation processes by double photoionization with a synchrotron radiation. Please, Marco.
Good morning.
Please.
Non eravamo là.
Sì, eravamo.
Ok.
Good morning, everyone. Marco Parriani. Today I will discuss about the data analysis of molecular peptides fragmentation processes by double photoionization with synchrotron radiation, which is basically my main PhD research topic. And I will specifically carry the example of the double photoionization of the alene gaseous molecules. So in brief, in our group, we focus on the study of ionized species, in particular on dications. But in general, the ionized species are really important, especially if we narrow the field of study into the astrochemistry and atmospheric chemistry, which are enormous fields, of course, but ionized species are involved in several processes of formation of complex molecules, as well as they are involved in applied science, as you can see, for example, from the image here of the ion thruster, which is a propulsor used in high vacuum, theorized in 1911. But remaining strictly to the process of formation of complex molecules, we can quote some notable examples. That can be, for example, trihydrogen cation, which is one of the most abundant ion in the entire universe. And it's involved in several reactions, forming a large number of intermediates like HCO plus or the H plus, but also molecular hydrogen and also water. Here is highlighted the formation process of water. And even if the main process to form water in the interstellar medium is still considered to be the one starting from dust grain, this is a really interesting process, especially because the trihydrogen cation is really abundant in the universe. But another example can be the study of one of the most interesting satellites in our solar system, which is Titan, with its hydrological cycle very similar to the one of the prebiotic and prebiotic heart. Just with methane instead of water, and it's really important for the presence of a numerous amount of molecules carrying a cyano group. One result that can we quote from our group is the study of the fragmentation of CO2, especially the Coulomb explosion of the CO2 plus molecular dication, observed using a photon energy range of 34 to 50 electron volt. And this study explained the scarcity of O plus fragment in the Martian ionosphere, which has been highlighted by Mariner 6 spacecraft and by One lander. And this was kind of strange because the atmosphere of Mars is for the most part formed by CO2. So this scarcity of O plus was a bit strange, but has been explained by us from the study of this fragmentation, which exposed a fragment O plus with an energy higher than the escape velocity from the atmosphere. So how can we do that? These reactions happens in the ionosphere or interstellar medium by the interaction of UV radiation in an extremely rarefied environment. So we can simulate this using, in our case, the angular resolved photoemission spectroscopy, or APES, which can use the high photon flux of a third-generation synchrotron source. In our case, we often work at the gas phase beamline of the Electra synchrotron facility in Trieste, working in high vacuum through this ion imaging spectroscopy apparatus, which is based on a photoelectron, photoion coincidence coupled to a time-of-flight mass spectrometer, and it's specifically designed to measure the spatial momentum components of the ion fragments produced in the experiment. So, in the on the left is shown a typical ion, coincidence plot. In which in red are reported the the time-of-flight spectra of the ion detected, and how it works. The sample is introduced with a stainless steel needle or a paralytic source inside the interaction chamber, in which we reach a high vacuum of 10 to the minus 8 or to the minus 7 most of the time. And the synchrotron light, once we cut the higher order of energy, intercept the sample in the interaction region, and the electrons generated are accelerated and act as a time-of-flight triggers for the ions, which are extracted, accelerated along the time-of-flight spectrometer, and selected in mass. So now, in theory, in the coincidence plot, every black point could represent an ion-ion coincidence. In reality, this is not exactly true because you need to subtract the background and the false coincidences. And if you focus just on the high density regions of the spectrum, you can associate every so-called island of coincidence to a peak on the spectrum 1 and on the spectrum 2. So every coincidence island is related to an ion-ion coincidence. So the dots are related to couples of time 1 and time 2 photoions delay times with respect to the detection of a photoelectron. And at each wavelength, you have the intensity of this channel of fragmentation that is given by the total counts for each ion pair. And instead, the dimension of the island and also the shape and the slope also of the island give the kinetic energy released for two-body reactions, or the energies of the observed ions for three-body reactions. So the example that I'm carrying is the one about Aline, which is the first member of the Coumadin series. We chose this molecule because in 2022 an experiment has been done by Pfeiffer et al., which is a group which we cooperate with. And it was based on the double photoionization of Aline at 2140 electron volts using a medium discharge lamp. So we decided to go deeper in this investigation, and we performed a double photoionization in the 2545 electron volt energy range on the gas phase and circular polarization line of the Electra synchrotron facility in Trieste. And we identified several fragmentation channels, as well as we evaluate the kinetic energy releases. But most of all, we identified 4 metastable traces in the energy range investigated. We chose this molecule also because it's quite interesting. It has not been directly detected in the interstellar medium, but it's theorized to be present in it. And it can exhibit stereoisomerism if substituted, of course. So on the left, you can see the 11 different fragmentation channels that we highlighted, and the ionization thresholds carefully analyzed and defined with the relative error. How we did that? This is a plot in which you can see the intensity of each island related to the corresponding channel, plotted in function of the energy. And we did so analyzing the dots, basically, inside every island for every energy, and subtracting the background and the false coincidences. And from the analysis of the number of coincidences as a function of the photon energy, it was possible to identify the exact energy at which the channel begins to appear. After that, of course, we used a model based on the Vannier function to define exactly the energy value relating to the opening thresholds and the related error. Another thing that we did is has been identify the threshold for the appearance of the molecular dication, which was in literature around 28 with electron volt with an error of 0.3. And we obtained a value that confirms the literature value. Is slightly different, around 27.8 with an error of 0.1 electron volt. And we did that by carefully carrying out a measurement varying the photon energy on the order of the 0.1 or 0.2 electron volt. Here on the left, you can see different coincidences plot at different energy, and here you can see, of course, at 25 electron volt that no channel is opened, and at 30, just the main channel is open, and of course, on the other one, you can see all the channels open. From the momentum distribution in the center of mass coordinate system, it has been possible to obtain the total or partial kinetic energy release in the dissociation process. In reality, we did that for the two-body dissociation process, because for a three-body dissociation process, the center of mass coordinate system is way more difficult to analyze. But we did that for the so-called momentum matching channels. And from the IO momentum distribution, we also extracted the photofragments angular distribution with respect to the radiation polarization plane. And we have been able to extract a parameter which is called beta parameter, which in our case is around 0.15 with an error of 0.13. And the beta parameter accounts for the direction or the orientation of the molecules along the polarization vector. So if it's around 0, it can tell us that we have an isotropic angular distribution. The most important result is the identification of these metastable traces. Here we have 4 metastable traces, one shorter than the others, and this can occur when we have a fragmentation reaction that take place in a time longer than the window time of the apparatus, which is 50 nanoseconds. And if we analyze carefully the tail, we can derive the lifetime for the dications leading to the dissociation reactions. So we use the Monte Carlo simulation to estimate the trajectory of the metastable tails and to define the lifetime. Of course, we used first value of lifetime to do an iterative fit, and this is the reason because for the shortest tail, it is still not possible to obtain a trustworthy lifetime, because we don't have the possibility right now to use a starter lifetime which is higher than 50 nanoseconds. So we are still working on it. And with the number of coincidences as a function of the energy, which is the plot on the right, it has been possible to compare the experimental data with the calculated one and to trying to find a better simulation for the trajectories and to find the most reliable value for the dication lifetime. Here you can see the comparison, and of course, again, for the shortest tail, you can see that experimental data and the theoretical data don't fit very well the experimental data. For the other one, instead we have a good fit, except for the last part, which is still going to be refined in the future steps. Here is reported the behavior for the main lifetime, the main metastable trace, which is the H plus C3, H3 plus channel. And we use the photon energy of 36 electron volts, and the dots represent the experimental results. The line instead is obtained with a simulation with 10 to the 6 trajectories. And we have plotted the number of coincidence points along the track of the data as a function of the difference in time. And we have fit the data by the Monte Carlo simulation of the ion trajectories in the mass spectrometer. After that, we tried to find the best value of the lifetime, plotting reduced mean square values of the difference between experimental data and simulation as a function of the dication lifetime. And we found the minimum obtained deviation as a lifetime of 160 nanoseconds with an error of 20 nanoseconds, which we think is coherent with the thing that we observed. So in conclusion, we expanded the knowledge about the fragmentation processes involving the double photoionization of the alene molecules. We confirmed the literal value of the appearance of the molecular dication, but most of all, we highlighted 4 different metastable tails, including the one regarding possible proton migration phenomenon, which is the shortest metastable tail, which needs further improvements. Next steps could be to add more statistics to define the angular distribution and kinetic energy releases, especially for a 3-body dissociation process, and to do a tailor-made simulation to account for the terminal part of the metastable tail for all the species, and to improve the study of the shortest metastable tail that could be the most important one. I would like to thank everyone from the staff of Space Beamline at Synchrotron Trieste, my university, and of course the organizer of ICCSA 2024 for the time.
Thank you, Marco. Is there some question from the virtual?
No.
Okay.
I have a curiosity, if possible. I don't know if you can show again the slides with all the fragmentation channels.
Yeah, I had this problem yesterday too.
No,
Can you put it in the presentation?
Are disappeared, slides.
Avevo nel computer la fa vedere, ma dopo non nel proiettore.
I mean, it's the same as.
No, vedi, non...
Maybe it's not
C'è un
a
problema.
duplicate, is
Don't worry, it's the same.
vabbè, we have time. If you can try,
Yes,
because
now
we
I
have
can.
time, because the next
Yes.
speaker, there is not here.
Just one moment.
Yeah, don't worry. Dopo le nostre cose.
Sì.
Non lo so, non ho visto.
Okay, sorry for the inconvenience, and here we are.
Okay.
This one?
Yes, this one. So my question was if there is theoretical investigation of the fragmentation pattern in literature.
Yeah, there is. I mean, the model that we use is based on on a function which takes into account some scale coefficients as well as the energy in electron volts. So we have four parameters, which are typically C1, C2, epsilon1, epsilon2. This depends if you chose a single threshold function or a double threshold function. If you chose, for example, but then it's empirical was because you base your analysis on what you have on the spectrum. So if you think that a double threshold model would fit better, you choose a double threshold model. And basically, C1 and epsilon1 are iterative, so you define a start guess, and then you define the energy as a dependent parameter. And from that, it's an iterative work to define the better value of epsilon1, because C1 defined the slope, and epsilon1 defined the intercept with the experimental data. So, I mean, if you have one flex point, you basically use a model with a single threshold. If you have two, you use a model with a double threshold, and you define the parameters. This because, I mean, it was there is a literature reference about the use of this model for the double ionization energy thresholds, because we could also use, I don't know, the partial derivative method to get the flex points, but this is based on a model used in literature. So we chose this because for example, Stefano Falcinelli was using this method in other experiments, so it's based on that. Yeah. But yeah, it's present in literature. Yeah. I think that in the abstract of the data presented for the Congress, it is present also the reference.
There's only this function. You don't have like fragmentation paths. I don't know if it's also meaningful at that point.
No.
Because the ionization is dissociative. You don't have the formation of the charge intermediates which then dissociate, right?
No, because that is a bit more complicated to analyze. Also, if you have an associative mechanism, I think that also the shape of the island will change. Okay. Yeah, there is also a study that is from Feifel group, which is about the different shapes of the island in referring to the different mechanisms that are occurring in the reaction. Yeah, I mean, you can have a butterfly shape or a banded shape. It's really vast.
Okay, thank you.
Thank you, Marco. Thank you. And we move to the next speaker that is not here. And I think that we needed to wait because just a moment. The next should be Marzio, and the next is Luca again.
So we can also skip to the fourth presentation.
But the last is virtual, and I don't know if the person is connected, so because in Italy is a little earlier.
I know.
So, if we want to move to the Luca, and wait to the...
Do you have... can you contact the speaker?
The last speaker, just about is too early.
I think I can.
But they know that they have to present at this time.
So?
They know.
No, but they know at 10.
Connect directly for
direct
I don't know,
gaze.
maybe I can have the talk and then if it's not connected. we
So
can
you can
continue.
see if he is correct.
Yes, he is not. He is
Because
not.
in Italy it's 5 o'clock.
Yeah, no, but he knows that he has to present
Yeah.
his paper
No,
at
he
5.
presented 20 past 10.
In 40 minutes.
It's in 40 minutes. Maybe he put
Ah,
it there.
okay. Ah,
So
okay.
now is the time of Marzio. Marzio
Yes.
is not
I
here.
know.
Move to
Yes.
Luca.
I guess it's
Okay,
thing to do.
Luca. So, thank you, Luca, again. Luca, now,
Yes.
okay, no, okay, it's not there. So, Luca will speak about the challenges of characterizing biomolecular reactions of aromatic compounds via computational chemistry. So, he will speak about the case of N plus pyridine reaction. Okay, Luca?
Please. Problem here. Okay. Okay.
Thank you. In this talk, I will try to focus again on reaction dynamic, but of neutral processes. And in particular, I want to focus on the possible difficulties of characterizing the potential energy surface of relatively big systems for our case, such as the one of atomic nitrogen with beryllium. These systems is particularly important for the prebiotic chemistry and in particular for the chemistry of Titan. So as we saw in the previous talk, Titan is considered one of the best candidates for the study of the prebiotic chemistry that led to the formation of important molecules on Earth. Titan is Saturn's largest moon, the second largest moon in our solar system, and it's quite peculiar, and it's been interest and focus of different space missions in the last year. The most important and fascinating one is the Cassini-Huygens missions, which allow us to have plenty of information about the structure and the composition of the planet and of its atmosphere. The peculiarity of Titan is that it has a thick atmosphere, mainly composed by molecular nitrogen as our own atmosphere. And the data from the Cassini-Huygens mission revealed that, as we said, the main component is molecular nitrogen with a percentage of around 90%, followed by methane, which is liquid on the surface and it has a sort of geological cycle as water in our planet, followed by a small amount of other carbon-rich compounds like HCN or saturated and unsaturated hydrocarbon. The temperature on the surface is around 94 Kelvin, and on the troposphere and thermosphere, which is around 1,000 kilometers of altitude, the temperature is 185 Kelvin, and the pressure is around 10 to the minus 6 millibars. So also in this case, the environment is extremely rarefied. But despite this quite harsh condition, a complex chemistry is acting. And the missions and the analysis revealed the presence of also macromolecules with a C-NH ratio of around 1:1. So here we have a scheme of the proposed mechanism and model to model the chemistry in Titan atmosphere. So the starting point is the dissociation of the main component like molecular nitrogen and methane by different energy sources, such as electrons, protons, ions, but also Saturn, magnetospheric electrons, and so on, leading to the formation of reactive species which can then meet the other molecular partners and form different molecules, including complex aromatic species, which are the main component of the orange haze, which is peculiar of Titan also from the observations. Finally, we are really looking forward to the new data about Titan, which will come from the NASA's Dragonfly missions, which has been scheduled and will take place around 2028. So hopefully in 4 to 5 years, we will be here to present again the new results of these important missions, which will be able to land on the surface of Titan once again after the Voyager missions. So as we said, the main reactive species is nitrogen. The main component is molecular nitrogen, but it has a high chemical stability. So in order to have the complex puzzle of Titan's chemistry, we have to look at active forms of nitrogen, which are ions, cations, dications, and radicals. And in particular, the interaction of molecular nitrogen with UV radiation or energetic particles lead to the dissociation of the molecule, leading to the formation of atomic nitrogen in both the ground state 4s and the first electronically excited state WT. But the ground state is not reactive with closed shell molecules, so the main reaction partner in this case is NWT, which is characterized by a high energy content of around 230 kJ per mole, and a long radiative lifetime of around 36 hours, which allows the recombination and the reaction with the different partners that are present in the atmosphere of Titan. Regarding aromatic species, we have plenty of detection of benzene and benzene radical. We have also the modelization of the abundance of these species as a function of the altitude of the atmosphere. And we can see that at around 1,000 kilometers, which is the thermosphere in which we have the peak of production of NWT, we have also the peak of the abundance of benzene. The situation of pyridine is a bit more complex because in principle it should be present because we have benzene, which can be considered also precursors of pyridine, considering the reaction with nitrogen or other species. But the last attempt to detect pyridine and pyrimidine has basically led to no results. So in principle, pyridine and pyrimidine has not been detected at the moment. But we are still looking forward for the detection because pyridine and pyrimidine are particularly important species from a prebiotic point of view because they are the sort of precursors of complex and also biomolecules like the structure. They are key component for the structure of DNA. So a huge effort is nowadays to detect pyridine and pyrimidine on Titan's atmosphere. So in this work, we focused on the reaction of NWT with pyridine, and in particular, we wanted to understand how we can treat the system, which starts to be relatively complex considering the dimension of the system and the method that we have, the method and the computing time and the resources that we have at the moment. So we wanted to understand which is the best computational strategy to treat the problem because the identification of the all potential energy surface is a key element in order to perform a kinetic analysis to derive reaction rate constant, channel specific rate constant, and branching fractions. We performed a benchmark analysis to identify the best initial strategy to derive the potential energy surface. We performed TFT calculation with different functional, the D3, the N062X, and the Omega B97XT, with two different basis sets, the global basis set and the more accurate triple zeta basis set. We derived the geometry of all the intermediates, reactants, and products in the portion of the surface that we wanted to study, the frequencies, and the energy. And we compared the energy with the more accurate couple cluster analysis performed considering an extrapolation on the complete basis set, which provides one of the most accurate values that we can have, but it's extremely computationally expensive. So we focus on a small portion of the potential energy surface, and we will see in a while why I say small portion. And in particular, we consider a bridge addition of atomic nitrogen to the, we can say, meta and para position, leading to the formation of a first intermediate characterized by a C and C three-body cycle, three-term cycle. We can see that the attack is direct. Here I report the potential energy surface considering the energy, the more accurate energy is obtained at the couple cluster CDS level. We have a direct addition mechanism, so the process is barrierless, and we have the formation of the first intermediate with one, which is located around 330 kJ per mole below the reactant energy asymptote. Once formed, the intermediate can easily dissociate to the neutral intermediate, which is lower in energy, and it's characterized by the presence of a 7-member ring in the structure to the breaking of a carbon-carbon bond. And we can see that the transition state here is related to a barrier which is very low, so the process in principle is faster, and is expected to be faster than the other possible isomerization process, which leads to the formation of an intermediate characterized by an NH moiety, in which the transition state is characterized by the breaking of a CN sigma bond and the transfer of the nitrogen atom from the carbon to the nitrogen. Once formed, the min2 and min3 intermediate can directly and barrierlessly dissociate to different combination of products, mainly related to H displacement channel. We have the formation of the P4, which is the most exothermic product channel, and the formation of 3 different 7-member ring species, characterized also in this case by H displacement process. So once we have identified the first steps of the potential energy surface and the mechanism that we wanted to focus in, we started the benchmark studies. And as first step, we perform an analysis on the geometrical parameters. So we consider three different stationary points: the reactant, the pyridine molecule, which is a singlet closed shell molecule, and two doublet open shell species, a minimum structure and a transition state. So we had, in order to have the full cases, considering both open shell and closed shell species and minimum and transition state. We analyzed the bond length and bond angle of the bond length and bond angle of the three intermediates of the three species. But we can see that considering the different functionals and basis set, we have no particular difference. So there is no huge effects on the geometry by using different functionals of basis sets. So our analysis should be moved to basically the energy and the value of enthalpy and barrier heights. So considering the same potential energy surface, the same reaction pathways, we evaluated the relative energies of all the stationary points, minimum transition state, and products, considering the reactant as zero, so as a reference. So all the energies has been scaled, considering the one of the reactants calculated with the different methods. And here we can start to see some effects. And in particular, we can see that we have a better match with the CCS, the TCBS energy, which is the reference, if we use the triple zeta basis set. So the use of a more accurate basis set leads, as we expect, to more accurate values of energy. And regarding the functional, also in this case, we don't have huge difference, but the main difference is related to the computational time and to the easiness in which we have the optimization of the structure. And we can see that the B3 functional, or alternatively M0628 functional, represents one of the best strategies for the analysis of this kind of reactions, mainly due to the difficulties that we have with the other functional to locate some transition states. We can notice also that the use of the omega B functional is one of the best choices in the cases of reaction with atomic oxygen. So if we deal with atomic oxygen, we have plenty of literature that shows that the omega B functional is better than the other one, but in the case of reaction with atomic nitrogen, we can use the B3 functional, which is a good compromise. We evaluated also the enthalpy changes and barrier heights for all the reaction pathways, and we can see that we have, here I report only the data obtained with the triple zeta basis set, which is the best choice. We can see some differences with respect to the CBS analysis, but we can notice also that even if the absolute values are different, we have a relative behavior which is basically the same, because in some way the energy of all the stationary point is lower within the same more or less range. So the path probability, which depends on the relative heights of the barriers, is not changes. So we can conclude that the best computational strategy can be the use of the B3 functional with the triple zeta basis set. We performed, in conclusion, a benchmark study of the reaction of atomic nitrogen with pyridine molecule in order to obtain, to understand which is the best computational strategies, which appears to be the use of the triple zeta basis set with the B3 functional. This is quite important because pyridine can be considered the precursors of more complex species. So reaction of atomic nitrogen can take place with other partners like toluene, like also species containing 2 or 3 aromatic rings, which are extremely complex to treat from a computational point of view. And here I report some snapshots of the full investigation of the potential energy surface of the pyridine that we performed, and we are preparing the article nowadays. We have six possible different attacks, considering the fact that the presence of atomic nitrogen on the pyridine ring leads to a breaking of the symmetry. So with respect, as example of the case of benzene, we have more possible attacks in the ortho and additions in the ortho, meta, and para position, and we have also the ipso attack, which leads to the formation of a direct nitrogen-nitrogen bond. Each one of the intermediates formed by the direct barrierless approach can isomerize and can dissociate in different ways. So we performed also RRKM calculations. So the strategy that we used here is a first analysis of the potential of the all potential energy surface at the Bitterlip level with the Mobile basis set. We perform a first round of RRKM calculations, which are statistical calculations to evaluate the branching fractions. And considering the most favorable product channel, we refined the calculations at the same Bitterlip level, but with the triple zeta basis set. We use then the new energies to perform a reevaluation of the RRKM analysis, and finally we calculated the energy of only the main product channel at the CBS level of theory. And it took a while and a huge computational effort. So with this work, we hope to identify the best strategies to treat more complex systems, and finally we compared our theoretical treatment with the cross-molecular beam results, which are obtained in the Perugia facilities, which allows to study reactions under single collision condition, so it's able to characterize the single reactive event without interference of any other molecules, since we work on high ultra vacuum conditions. And we have in this case a good agreement between theoretical prediction and experimental analysis. So if you want to have a picture of the overall system, stay tuned. We are about to submit the paper in these days. So thank you for your attention.
Thank you.
I have a question that's more of a curiosity. I mean, I understand that the pyrimidine are in gaseous form for the
Yes.
computational study. I think also for the computational cost of the analysis.
Yes.
I think. But it would be useful or possible. I don't know if I don't know about the exact chemistry of Titan. So to imagine maybe a solvatation shell for the pyridine, maybe because there are methane seas on Titan. So I don't know.
So for the specific case of Titan, I don't know if there are works considering solvation. The process on, let's say, condensed phase is particularly important for the interstellar medium, and from a computational point of view, there are models to treat basically the surface of the ice. So we have a cluster of water molecules in which the two reaction partner can be stored and react together. So there is a group in Torino that studied the group of Professor Piero Liengo, as example, that studied the best way to represent the cluster. And if I remember correctly, it's with 18 or 23 water molecules. So they built the cluster of water molecules and then they let the species react on the surface. I don't know if it can be done also with methane.
Okay, thank you. So we wait for the next speaker
Okay.
in about 13 minutes, so we can stop
Sì.
the...
Non so se prima fosse connesso
session.
perché ho visto
No.
una so che condizioni, ma è dato proprio l'ennesimo anno.
Good morning, Professor Giustini. Can you hear me?
No, ci vediamo, grazie.
I can hear you.
Hello,
Okay.
hello, Andrea. Hello, please, can you open turn on, okay? Try to speak because there is something about the sound.
Can you hear me?
Yes, like a metal. But, I don't.
Yes, we can hear you.
Maybe it's, just a moment.
Okay. Forse così va meglio. Can you try and speak again?
Good morning, everyone.
No. Puoi abbassare un pochettino, Andrea, il volume perché ti sentiamo tanto metallico e proprio non posso, cioè,
Sì, può darsi che sia il suo microfono.
hai delle cuffie o
Le cuffie, sì,
se
ma
c'hai
funzionano.
delle cuffie che ci abbiano il microfono perché ti sentiamo?
Un momento.
Ok,
Credo che sia il microfono in Italia.
non c'è niente, perfetto, perché così io dopo verrò cioè adesso c'è Clari. Sì. Devo vedere se c'è una chiavetta dentro. Tu ce l'hai. Direi che risposta sta.
Un minuto perché non è semplice collegare queste cuffie. Un minuto.
No, Andrea,
No.
non ti sentiamo. No.
Pazienza, se...
Sì, senza togli quelle cuffie. Va bene, dai, abbassa un pochetto il volume perché noi qua te sentiamo tanto alto, così tu puoi fare.
Faccio un'ultima prova. Adesso com'è la situazione?
va bene.
Così va bene, dai, prova a condividere le slide.
Perché non mi... Aspettate. Oh.
Qual è il problema?
Non riesco a condividere. Un momento.
Conviene
Ma,
condividere l'intero monitor.
Ecco.
Ok.
ok, mette la modalità presentazione, no? Meglio, no? Ok, meanwhile I introduce Dr. Andrea Giustini from Department of Environmental and Civil Engineering, University of Perugia. Inside of the Beyond 2P Print project, he will speak in the fossils, Migliora and ASI. Italian Project of Fossil Biology, no ASI. He will speak about theoretical insights of the sulfur plus water reaction and their implications on the chemistry at the surface of ice in the interstellar environments. Please, Andrea, put in a slide in presentation way.
They already are.
No.
No?
No, I think so that you need to duplicate the display because so we will see the PowerPoint, I think so. The PowerPoint, okay, try again.
Okay, wait a second. Okay, you see the PowerPoint.
Okay, now try to put in presentation view. Okay.
The small icon close to the zoom bar, bottom right.
In the bottom part, in the right part.
Okay, what you can see it right now?
In the no,
In the PowerPoint.
Yes, we can see the PowerPoint, but you are not in full screen mode.
Go to the bottom part of the PowerPoint.
Yeah, bottom left, but I have seen
Bottom
the
right.
Zoom.
Bottom right.
Bottom right.
Oh, bottom right. Okay, but I don't have anything right.
Yes, there is 1, 2, 3, 4, 5 symbols in the symbol near to the zoom bar.
No,
Perché lui è in
Lui è già in
presentazione. Deve
presentazione.
uscire la presentazione, forse fanno...
But Andrea, you see your presentation in presentation view?
I can see my presentation view, and I don't have anything on the bottom right. I have something on the bottom left.
Okay. No, I understand, but you have duplicated the display, or you have the fall of the continuous display.
But where I can duplicate my display?
I don't know, in your computer you have some settings, display settings.
Okay, so I have to go to my computer settings. Okay, let's see.
Okay, don't worry, you can do it in this way. Try to move the slide, move to the next slide.
I'm trying to duplicate my screen. Let's see if I manage to do that. Okay, I have duplicated. So now let's start again. So tell me what you can see now. Still the PowerPoint?
The same. Try to do in this way. So move to the next slide. The second.
Nothing.
You need to go exit from the presentation.
my God.
Okay, so
Okay.
go. Start from this in this way. Go the first, okay, I have introduced. Can you start? Thank you.
I'm trying to do the last thing. Let's see. Still, you see again the PowerPoint
Yes.
and now the
Yes.
presentation. The same, just the same. Okay, let's
Same,
start.
the same.
Let's
It
start
doesn't
this
matter.
way.
We can go on. We can proceed.
Yes, go on.
Otherwise, we run late.
Yeah. Okay, sorry about that. So, yeah, I'm Andrea Giustini. Good morning, everyone. And my research area is focused on gas phase reactions in extraterrestrial environments. I used to perform kinetic calculations and electronic structures calculations in order to study these kind of reactions. And today I will talk about a theoretical investigation on the reaction involving sulfur singlet D, so electronically excited sulfur atoms, and water, and the relative implication of this reaction on the chemistry of the surface of ice in interstellar environments. But before diving into the interstellar environments, so before talking about this reaction in interstellar environment, I'd like to kick off my talk by introducing with a brief introduction about sulfur species in our atmosphere. Sulfur can be found in the atmosphere essentially as carbonyl sulfide and sulfur dioxide at the average concentration of 500 ppt and 1 ppm, respectively. And those species get released into the atmosphere mainly due to anthropogenic activities and volcanic eruptions. Once they reach the upper layer of the troposphere, carbonyl sulfide may dissociate. Following a reaction may result into sulfur dioxide formation, and sulfur dioxide formation may hydrate, so may react with water to form sulfuric acid aerosols. These aerosols, little by little, can increase the dimension. So they coagulate with each other. Once the size is very high, they start descending from the upper layers to the lower layers of the troposphere. And in this descending process, they can be absorbed by water droplets, or they can eventually provide nucleation centers for new water droplets to form. What happens is that sulfuric acid, of course, may acidify water droplets, resulting into acid rainfalls with all the bad consequences associated with this phenomenon. By introducing this slide, I want to shine a light on a controversial topic that is lately arising, coming up, which is the use of sulfuric dioxide and sulfur species in general for stratospheric aerosols injection. Because scientists saw these aerosols that can mitigate the effect from the global warming, because they have a very strong reflectivity power, or as you can say, shielding power towards the solar radiation, just as carbon dioxide towards Earth radiation. Obviously, this is a controversial topic, as I said, and an accurate evaluation of all the actual benefits, besides maybe it is more important the potential side effects, associated with this kind of application should be carried out. For instance, the potential side effects towards the stratospheric ozone layer that we all know it is quite labile. Okay, we leave the atmosphere, we go up to the interstellar environments where sulfur is mainly found, can be found mainly as hydrogen sulfide. And again, we find here also sulfur dioxide and carbonyl sulfide. We can find also carbon sulfide, thiophosphohaldehyde, and so on. All these species listed in this slide. They have been detected over the past few decades on a variety of interstellar environments. However, despite sulfur being the 10th most abundant element in the universe, the possible reservoir in dark molecular clouds is still unknown. Dark molecular clouds are denser region of our space, of our universe, where star-forming regions can be found within. So the scientific community is quite interested in studying these regions of our space because there is an intense chemical activity. As I said, in these denser regions, the abundance of sulfur is up to 0.1% with respect to the atomic sulfur in the diffuse interstellar medium, where sulfur can be found with a relative abundance of 0.0015% with respect to hydrogen. So, what is the possible reservoir responsible for this observed depletion? Experts at the beginning thought that it might be found as hydrogen sulfide on the surface or the bulk of interstellar icy grains. Although spectroscopy measures have not detected so far. Then they thought that the hydrogen sulfide can be photolyzed by cosmic rays, resulting into polysulfanes or sulfur polymers. But again, those species have never been detected. A publication date back to 2002 suggested the hydrogen sulfide as the likely reservoir, but following investigation, never proved, never demonstrated a similar depletion for iron as for sulfur. So, as you can see, there is a big question mark when it comes to talk about sulfur in interstellar, not in interstellar environment in general, but in dark molecular clouds, so in denser regional interstellar environments. And it is quite outstanding the fact that it is the only element in the universe showing this kind of problem, which is an unresolved problem. So, as a research group that deal with gas-phase reactions, we wanted to contribute in such regard by studying a very simple reaction involving sulfur. This is a preliminary work, so we started with this simple reaction. I'm talking about the water plus sulfur singlet D reaction. And we decided to take into account this reaction for three reasons. The first one is that it is a reaction that has never been studied so far, neither from an experimental nor from a computational point of view. Second, it is a reaction that is very likely to occur in extraterrestrial environments because there is a lot of water. Water is the second most abundant molecule in the universe. And the last but not the least, sulfur singlet D is a very reactive atom, and it is so reactive that it can insert into already preformed chemical bonds, giving rise to insertion reactions. We have also addition reaction in this system where the sulfur singlet D can add to the lone pair of oxygen. So we got mean 1 and mean 2 that are two intermediates, and then these intermediates can isomerize to mean 3 as well. And so this is the potential energy surface that we got. That's been calculated with the coupled cluster method. We're using the augmented correlation consistent PVTZ basis set. And highlighted in red, there is the only exothermic pathway that we got. All the other pathways arising, dissociation pathways arising from the intermediates are endothermic, so they are not thermodynamically feasible in those environments. Okay, interstellar highs, just because I mean, we don't have just gas phase chemistry, we also have condensed phase chemistry. This is something that is a little bit out of our research area, research of interest, because I mean, we used to study gas phase reaction, but it doesn't mean that there is no scope of action. I mean, we can face such kind of calculation, and also because, as I say, the interstellar highs are quite relevant. There is a lot of chemistry in condensed phase. Interstellar highs, in fact, can act as a pre-concentrator of chemical species on their surface, where those species can diffuse and eventually react. And this chemistry is quite important in low density environments. Interstellar highs could also offer collisional partner to dissipate the energy released from the molecular reactions occurring on the surface of icy grains. And in this scenario, the highs provides a stabilizing effect. Interstellar highs, and this is quite outstanding, has been proved by other research groups in the past. Interstellar highs can act as a catalyst thanks to the cooperative effect of the hydrogen bond network. I mean, I'm not talking about any reaction. Of course, there are reactions that are favored more than others. So we took into account, so to make a long story short, we tried to simulate this system, the potential surface reaction, by considering a four-water molecules cluster. You have to think of it just as the reactive site of the surface. So what happens is that sulfur atoms in the gas phase can be absorbed by the highs, the surface of the highs. And in this system, of course, it can react just with water. You can see you can count up to 5 water molecules just because one water molecule is regarded as one of the reactants. You have also here additional reaction and insertional reactions, but unlike the isolated system, the gas phase system, a lot of dissociation pathways are completely inhibited from a mechanistic point of view. And so we got just 2 sets of products consisting of hydrogen displacements. And these sets of products are also quite borderline because they are at the same energy level of the reactants. And this potential energy surface has been calculated at the B3 leap functional. So we are planning to perform higher level calculations in order to make sure that these pathways are indeed thermodynamically active. Here you have a B3 leap, an enhanced overview of the B3 leap optimized structure of intermediates. Also, you have the transition state optimized, and these are the imaginary frequency. I mean, I don't have the presentation on, so it's quite difficult to let you see. But anyway, this is the vibrational frequency analysis that resulted from the calculations. As you can see, there is this shifting of hydrogen from an atom of sulfur to an atom of oxygen or vice versa. So I don't know why. Okay. So in conclusion, the water molecule cluster, we could see that the water molecule cluster affects the reaction, preventing some of the pathways, some of the channels active in the gas phase from occurring. On the contrary, gas phase non-active channels become thermodynamically active in the presence of the four water molecules due to a stabilizing effect of the cluster. But we have to make sure about this. So in the next future, we are planning to perform eigenlevel calculations, for instance, at the couple cluster level of theory. And also the idea is to increase the cluster size in order to detect the potential catalytic effect. So I'm done. Thank you for your kind attention. Sorry for all the issues. And of course, if you have any question, I'm here to answer. Thank you for allowing me to present at this conference.
Thank you, Andrea. Okay, I don't know if there is some question in the virtual room. It's not any question. I have some curiosity. Have you decided if you evaluate the rate constant and if the answer is yes, which method will you use?
I didn't get the question. You are asking me if I tried to perform kinetic calculations to
Yes,
calculate the
the
rate
rate
constant.
constant. The rate constant.
No, we didn't. We are not interested on the kinetics at this moment for this system. I mean, probably we will try to calculate the rate constant for the isolated system, but for this system we are just trying to see if the ice is able to affect the reaction, and we actually saw that there is this chance.
Okay, thank you, Andrea. If there is no any more questions, thanks, Andrea, for the recap earlier, and thank you very much. We conclude the session. See you at Perugia. Bye bye, Andrea.
See you.